Hello, welcome back to the Geog 300 Geographical Data Analysis video series for WVU. In the previous video, we looked at two different density-based approaches to understanding are my points random, even, or clustered, working off of that first assumption of complete spatial randomness. The idea that some places are more or less likely to house points, have points located there, than under the assumption of randomness. Distance-based approaches focus on that second version, that second assumption of complete spatial randomness, that the points are located independently of each other. So now we are, in a way, not looking directly at where the points are in the study area. We're looking at, are they close to each other or far apart from each other? The first approach to this is looking at the distance between pairs of points. Is to say, how far is a point from its nearest neighbor? Hence, nearest neighbor analysis. So for every single point here, I say, how far is it to its nearest neighbor? Sometimes, if those points are really close to each other, they will be each other's nearest neighbor. That is not guaranteed. The same way, the idea of k nearest neighbors as the weights matrix for spatial autocorrelation wasn't symmetric. So sometimes this point here, its nearest neighbor is here. But these 2 points are the nearest neighbor to each other. Likewise, this will point there. This might point there. So I measured the length of every single one of those arrows. That would be the distribution of all of the nearest neighbor distances. Okay, it so happens that we can, again, with complete spatial randomness, find the distribution for what I expect those to be and use that information So what I can then do is to say, and the normal distribution eventually gets involved. What do we need to know to understand the normal distribution? A mean, and either a standard deviation or a standard error. We're going to be working with the standard error here. Although that's based upon the standard deviation. So I first want to find the average of these distances. To be clear, the mean. I want to say that is the mean, using the bar to denote the mean, of the nearest neighbor distance. So we might use this particular notation, sigma of nearest neighbor distance, that just uses this number, 0.26136, divided by and it's based then divided by the square root of these two numbers multiplied together, n and lambda, n being the number of points. So as you get more points, then basically we have a bit more confidence that our average distance to the nearest neighbor is close to this sample. In a sense, we can think of this as a sample and this being setting up the confidence interval. If I have more points, then my confidence interval gets closer. The other thing affecting that interval is the density of the points. If I pack in more points, the density increases. Not only, if the density increases, not only does the average distance kind of have to decrease, the amount of variation that mean nearest neighbor distance can have also decreases. So it's sort of like you pack more things in, there's less wiggle room for that. If we, I know it would be more evenly distributed than random, but it's sort of like if you have a really empty ballroom and you only put in 5 people, they can remain socially distant from each other and have a whole lot of wiggle room that they can move about. As you pack in more and more people, it's harder for them to move around and still maintain that 6-foot social distance. As the density increases, the amount that the average distance between 2 points, between 2 people there, that average distance has to get closer and closer and not have much flexibility. So we have, as the density of points increases, as the number of points increase, both of these reduce the standard error. And this formula is how we end up going about calculating that. So if we think about the z-test, we had 3 parts to that: the mean, the standard error, or standard deviation, and what the expected mean would be under the null hypothesis. This third part we'll put it as NND of R for random. It's based solely upon the density of the points. Specifically, 1 over 2 times the square root of lambda. And it'll be clear that this refers again to that. So now I can do a z-test. We saw that before. We think back about to see, is a particular value an outlier? It was like the first example of an inferential hypothesis test that we did. That comes back here. So our z-test was comparing our value against what's called a standard normal distribution. The normal distribution with a mean of 0, a standard deviation of 1. Our z-scores created that for us. This does the exact same thing for this particular statistic, this particular value. Take our actual mean, subtract off what we expect under randomness, divide by that standard error, and we can now check against this particular distribution for the null hypothesis. If I have a value out at the tails of that distribution, it ain't random. It doesn't fall under this distribution. If it is towards the middle of the distribution, then I can say I follow complete spatial randomness. If I go and I reject the null hypothesis of complete spatial randomness, I can then look to see, is the average distance too long? Is the average distance longer than it should be compared to the expectation of randomness? If the distance between 2 points is too long, then they're spread out. That means they're even. If that distance between 2 points, distance from a point to its nearest neighbor, is too close to each other, then I am looking at a clustered situation. Because they're all bunched up together, they're close to each other. The nearest neighbor distance is too short for randomness. So that is this nearest neighbor statistic. Now, one limitation of this is that we're only using the distance to the closest, the nearest neighbor. There are a lot of different pairs of points here, a lot of distances that we are not using. If instead I want to use every single distance, every possible distance here, I have a different technique I can use called Ripley's K function. So at first glance, this might remind you a bit of the semivariable. It's not quite. But we do have the distance between each pair of points here. The distance between pairs of points. And the number of pairs the total number of pairs, and I'll put total just to be very clear, closer than that distance. This is going to give us a function. That function is going to start out at or very near 0. But I can then go out and say, okay, there's some here that are really close to each other. So that's going to go up fairly quickly. There's not a whole lot of an intermediate distance. And throughout, I can say, okay, at any distance, how many pairs of points are closer than that? So I graph this out. There is then some uncertainty in that. And basically, how do I assess the significance or the p-value of an entire function? That's kind of hard to do. And what we end up working with is, again, Monte Carlo simulations. So where I randomly put those points. I just do that, again, that bad darts player example. Put them anywhere in the study area. And figure out what this function is. If they are random, this line is going to go up straight as a diagonal line. But what's the confidence interval around this diagonal line? That's where these Monte Carlo simulations come in. And I can say, for any distance, I can get I'll call that K for random, and have a confidence interval around this diagonal line. So for most of what I have here, this green line is mostly inside and is therefore a randomly distributed set of points. The exception is here. I dip outside that expected line briefly. In this case, going above. That's saying that at these very short distances, there's actually more pairs of points closer than that than I was really expecting there to be. At which point they're clustered. Because there's a lot of points closer than that than there really ought to be. If it goes on the other side, then there's there's not enough points at that distance or shorter. If I get to a point where there's not enough points at that distance or shorter, they're too far apart again. So if the actual line extends beyond this confidence envelope in dipping below it, then it is even. So in this case, I could say, for the most part, these points are random. But at really short distances, within this particular I'll say D sub CL for the distance of clustering, shorter than that, they actually are clustered. So this Ripley's K allows us to give a particular set of additional information to say they're clustered. It goes above this line at some point. There is clustering involved, and here's the scale of that clustering. We could even put a kind of a complex sort of bizarre scenario, but it could happen, of randomized to evenly spaced clusters. If I do just the nearest neighbor analysis, this will be extremely clustered. Ripley's K would do kind of like this. And could actually recognize by saying, here at short distances it's clustered, at longer distances they're evenly distributed, and recognize this peculiar situation of evenly distributed clusters. Furthermore, in something like this, if I set up my quadrat grids correctly, it may say by quadrats, they're evenly. Every single cell has 2 points, evenly distributed. Nearest neighbor says they're clustered. Not, so we have now 4 different approaches, 4 different tests. We have the nearest neighbor statistic, we have Ripley's K, here as 2 distance-based methods. We have the variance to mean ratio, we have quadrats with chi-squared as density-based methods. There is no requirement for them all to agree because they are approaching this question of, are my points even, random, or clustered? They are all approaching them from a slightly different perspective. That means for certain peculiar non-random patterns, they may not agree with each other. Since the value of perhaps doing additional tests, not just relying upon a single one of these statistical tests. So that is an overview and illustrating 2 distance-based methods. As always, if you have questions, please feel free to ask in class. Feel free to reach out by email, and we could potentially set up an additional Zoom session for one-on-one tutoring, whatever is needed to help you understand this material. As always, thank you for watching, and have a good one.